Welcome viewers, in this video we will see the transformer on no load. When the transformer is no load, what is the parameters available? Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we will see the topic. A transformer is said to be on no load if the secondary is open. We know that in transformer we have primary winding and secondary winding. If the secondary winding is kept open, then it is called as a no load. When primary is connected to the alternating voltage and alternating current is flowing, which produces alternating flux. So the secondary winding is kept open, primary winding is connected with the alternating voltage, so that alternating current flows. Due to rate of change of this alternating current, alternating flux is produced. So the primary input current I0 at no load is used to supply. So the little bit amount of primary current will flowing, because secondary is still open. So the load is not available, but only few little bit less amount of current is flowing in the primary winding. That is due to, one is the two components available. One is for iron loss in the core, due to iron loss, that is hysteresis and eddy current loss. Another part is very small amount of copper loss in the primary, right. So one is for iron loss, another one used for the magnetizing the coil, that is nothing but a copper loss. So this I0 behind the voltage V1 by an angle of pi naught, which is less than 90 degree. That is due to inductive circuit, current and voltage, current is lagging the applied voltage. So that is lagging by pi naught, but it is less than 90 degree. So at no load, the input power is W naught equal to V1. This is the applied voltage. I naught is the small amount of current flowing through the coil. Then cos pi naught. It's angle between V1 and I naught. This pi naught is the angle between V1 and I naught. Now we will see that this is again splitted into two components by referring the vector diagram. I naught cos pi naught, I naught sin pi naught. Right. Now we will see this diagram, vector diagram. So this is the flux, is a magnetizing current. This I naught is now splitted into two parts, magnetizing current and working current. Magnetizing current is flow is due to the flux. Due to flux only the magnetizing current is flowing. Due to magnetizing current only the flux is produced. So both are in phase. So applied voltage and sum of these two is the current. So that is, it is an angle of pi naught. So this magnetizing current in phase with the flux, this working current is in phase with the voltage. The vector sum of these two is nothing but a output current, is nothing but a primary current I naught. So this angle is pi naught. So based on that, this triangle is drawn separately here. So this is the I naught. This is horizontal component is the magnetizing current, vertical component is the working current. This is the total current in the primary winding. So this triangle is drawn separately here, right. So from that, if you take cos pi is nothing but opposite side by adjacent side, I mu divided by I naught. So I naught. So from that, I naught sin pi equal to I mu. Similarly, cos pi naught is adjacent side by hypotenuse, IW by I naught. So that I naught into cos pi will give the IW. So that the two components are available. I naught, there are two components available, working component and magnetizing component, right. So this induced EMF E1 and E2 are opposite to that of V1, because based on the Faraday's law and Lenz's law, induced EMF opposing the cause producing, opposing the flux, so that it is available in the opposite direction, right. So this is the flux available. The magnetizing current is in phase with the flux. The working current is in phase with the voltage. Vector sum of these two is I naught. That I naught and V is having then phase angle of pi naught, right. So that is given in the power V1 I naught cos pi naught. So these two components can be calculated from this triangle. So this triangle is drawn separately here. Based on that, we have I naught equal to cos pi naught, I naught cos pi naught equal to IW, that is cos pi naught equal to IW divided by I naught. I naught is multiplied here. So, this is called a working component or iron loss component. It is supplies the iron and copper loss in phase with the voltage. Another one, I naught sin pi equal to I mu. So, this is a magnetizing component. So, the little bit of current used for magnetizing component, it is a wattless component at which 90 degree, it is in 90 degree with the V1. It is used to produce the flux in the core, right. So, the one part of current is used to produce the flux in the core, another part is used as a iron loss component. The sum of these two, vector sum of these two is nothing but a total current in the primary winding. I naught equal to square root of IW square plus I mu square. Working component iron loss, this magnetizing component in the primary winding. Vector sum of these two is I naught. So, in this video we discuss about when transformer is on no load condition, what is the vector diagram and what is the current flowing through the winding. Subscribe the channel for more videos and notification. Soft copy of this material available on the drive. Link is given in the description box. Thank you for listening. Welcome viewers, in this video we will see the transformer on load. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we will go to the topic, transformer on load. A transformer is said to be loaded when the secondary circuit is connected to the load. When the secondary, we know that from the transformer we have primary winding and secondary winding. If the secondary winding is connected with the load, then the transformer is said to be loaded. The transformer on load. The magnitude and phase of secondary current I2 with respect to the secondary voltage will be depends upon the load. Whether it is in phase or it is out of phase, that is depends upon the load. That is the relation between the secondary current and secondary voltage. For example, I2 is in phase with V2, that is secondary current and secondary voltage, both are in phase. If the load is purely resistive, we know that the resistive load, current and voltage are in phase. If the load is inductive, the current I2 lag behind the V2. Secondary current is lagging the secondary voltage. Suppose if the load is capacitive, the current I2 leads the V2. Secondary current is leading the voltage. So, depends upon the load, it may be in phase for resistive load, lagging for inductive load, current is leading in capacitive load. Now, we will see what is the transformer on load. Refer the diagram. So, here we have the iron core is available. The square type iron core is available. So, this is nothing but primary winding, this is secondary winding. The primary winding winded on one side of the core, secondary winding winded on another side of the core. Here the V1 is the applied voltage applied to the primary. V2 is the voltage available at the secondary, but here it is not loaded. The secondary is open circuit. Secondary is not connected with any load. Initially it is not connected with any load. Only the primary side the voltage is given. When the voltage is given, the one small amount of current I naught will flowing through the primary winding. This is due to producing the flux in the primary winding. The no load current is nothing but I naught. No load current flowing through the primary winding is called current called I naught. This is due to the producing the flux in the primary winding. Without any load, only small amount of current flowing for magnetizing the primary winding, that is called I naught. So, due to this magnetize, the flux is produced in the primary winding. The flux is following the iron core. This iron core is square type. So, the flux also flowing in a square manner. That flux linked with the secondary winding. But the secondary winding is open circuit, so no current is flowing through the secondary winding. So, this is coming under no load condition. The secondary is not loaded, only little bit of current I naught flowing in order to produce the magnetic field in the primary winding. Suppose if the load is connected, now we will see this under no load condition, a voltage V1 is applied. in primary winding. So the current I naught flowing which set up the flux pi in the circuit. This pi is nothing but a main flux, the main flux produced in the circuit, the no load condition. Now we'll see what will happen if it is loaded. If the secondary is loaded, what will happen? See this, now the primary is connected with the voltage V1. Now secondary is connected with the load. The secondary is now closed circuit. The secondary is now connected with the load. So what will happen? The secondary current I naught will flowing through the secondary winding. The previous case the secondary is open, so no current is flowing in the secondary winding. Only little bit of small amount of current I naught flowing in the primary winding. Now secondary is loaded, so current I2 is flowing in the secondary winding. This I2 will produce the flux pi 2 because this I2 is rate of change of current. The current flowing through the secondary is rate of change of current. Due to that, pi 2 is flowing, pi 2 is produced in the secondary winding. See the direction, the pi 2 is opposing the main flux. You see this direction, the main flux is coming in this direction. This pi 2 produced by I2 is opposing the main flux. So that is given. When the secondary is loaded, a current I2 is flowing in the secondary. I2 set up the flux pi 2 which oppose the main flux. Right? So this pi 2 is nothing but the flux produced by I2 that will oppose the main flux. So due to that, the main flux decreases, then E1 also decreases. So due to opposing of this pi 2, the pi value main flux is decreasing. So that EMF induced in the primary winding is E1, that also decreases. Suppose if E1 is decreases, what will happen? Now V1 is greater than E1. The applied voltage is greater than the EMF induced. So that will cause more current to flow in the primary winding. So due to the V1 greater than E1, more amount of current is flowing through the primary winding, that is called I2 dash. Already I naught is available. I naught is the current due to no loaded condition in order to produce the flux in the primary winding. Now secondary is loaded. Due to loading, I2 current is flowing in the secondary. That I2 current produce the pi 2 dash flux in the opposing the main flux. Due to that, main flux reduces, E1 reduces, so V1 is greater. Due to that, the more amount of current is flowing called a I2 dash. So I2 dash is the current due to the loading of secondary winding. Already I naught is available. So this I2 dash is anti-phase with I2. See the direction, this I2 dash is flowing in this direction, which is I2 is both I2 and I2 dash are oppose each other. This I2 dash will produce its own flux pi 2 dash. See this direction of pi 2 and pi 2 dash both are opposite direction. So it will cancel each other. So what will happen? The main flux phi remain in the constant. So that is our important thing. The main flux remain in the constant. The flux pi 2 dash produced by I2 cancel this pi 2. Both are almost equal and opposite. So cancel each other. So that make pi is remain in the constant. So I2 dash in anti-phase with I2. I2 dash set up the flux pi 2 which is equal in magnitude pi 2 but opposite to I2. Opposite to pi 2. So they cancel each other. So the resultant flux is constant. So that is the important thing. I will explain again. So initially the secondary is not loaded. Only small amount of current I naught is flowing. That is used to produce the flux in the used to magnetize the primary circuit. When the secondary is loaded, I2 is flowing through the secondary. This I2 will produce the pi 2. That pi 2 will oppose the main flux. So due to that, induced EMF reduces. But V1 is greater now. So that it will produce one more current I2 dash. That I2 dash will produce the flux pi 2 dash. This pi 2 dash and pi 2 are both are equal and opposite magnitude. So cancel each other. Finally, this pi is maintained constant. So that we are getting the constant flux in the transformer. Now we will see the equations. The total primary current is nothing but vector sum of I naught and I2 dash. I naught is due to no loaded condition. I2 dash during loaded condition. The magnitude of pi 2 equal to magnitude of pi 2 dash. Both are equal and opposite. The current I2 set the MMF is N2 I2. The current I2 dash set up the MMF is N1 I2 dash. Because see that this I2 is flowing through the secondary winding N2 and I2. This I2 dash is flowing in the primary winding, so that N1 into I2 dash. Right? So both are equal, so that N2 I2 equal to N1 I2 dash. So from that I2 dash equal to N2 by N1 into I2. So this N2 by N1 is nothing but a transformation ratio K. So that N2 by N1 equal to K. So that I2 equal to K times of I2. I2 dash equal to K times of I2. Right. So based on this, the current I2 set up the MMF in the secondary, so that N2 I2. So I2 dash is the current flowing in the primary, so that it is N1 I2 dash. Both are equal. So while equating by simplification, we got I2 dash equal to K times of I2. Right. We will see the total current. What are the current flowing? So the component of primary current. So that's called I1. No loaded condition we have I0, loaded condition we have I2 dash. So this I1 is the vector sum of I0 and I2 dash. What is this I0 during the no load condition? Like this for the magnetizing. Also it is having two components. One is for magnetizing component I mu magnetizing, and another one IW working component is called a iron loss. Some amount will be lost, that is called a working or active component, or otherwise called a iron loss component. Right. So the total current I1 in the primary is sum of I0 and I2 dash. I0 having two components, one is used for magnetizing, another one iron loss, that is called a working or active component. So in this video we discuss about when the transformer is loaded, what will happen to the current and fluxes. Subscribe the channel for more videos. The soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the phasor diagram of transformer on loaded condition. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we will go to the topic transformer on load. For that we can see the phasor diagram. The transformer on load, that topic is available in the separate video. For that also link is available in the description box. Now we will go to the phasor diagram. So we have the resistive load and inductive load. Capacitive load also available, that see later. First we will see the resistive load and inductive load. First we will see resistive load. So during no loaded condition, we will see that first no load condition, the current I0 will flowing through the primary winding. When the secondary is not connected with any load, that is called a transformer on no load. So at that time the current I0 is flowing, any small amount of current I0 is flowing in the primary winding. Now we will see that V1, we will take this V1 is the primary applied voltage, we will take this is the reference. We will take the primary applied voltage V1 as reference. So this no load current I0 having two components, magnetizing component and working component. Magnetizing component is nothing but it is the responsible for producing the magnetic flux in the primary winding, even the no loaded condition. IW is the working component, that is nothing but iron loss. This iron loss is in phase with the voltage. This magnetizing current is 90% out of phase, 90 degree out of phase. So due to this I mu flux is produced. So both are in phase. So we will take this V1 as a reference. During no load condition we got I0. I0 is the vector sum of IW and I mu. IW is the iron component or working component or active component, that is in phase with the applied voltage, but the magnetizing current I mu is out of 90 degree out of phase with the V1. This I mu responsible for producing the flux pi. These two are in phase. Now when the transformer is loaded, if it is loaded, what will happen? this I2 dash current will flowing through the primary winding. So this I2 dash also in phase with the voltage. But total current I1, this I2 dash is due to the loaded. When the transformer is loaded, I2 current will flow in the secondary. That due to that, one more current flowing in the primary is called a I2 dash. So the total primary current is nothing but vector sum of this I2 dash and I0. See this I0 and I2 dash both are added together, so that we are getting the total primary current I1. So because of resistive load, this I2 dash and V1 are in phase. Both are in phase. The current and voltage, primary current and voltage are in phase because of resistive load. So that we have another term I2. I2 is nothing but current flowing in the secondary winding, that is opposite to that of primary winding. What is E1 and E2? The EMF induced in primary winding and secondary winding. So based on the Lenz's law, the EMF induced is opposing the cause producing, that is opposing the flux. So this is the applied voltage, this is the EMF induced. So based on Lenz's law, both are opposite to each other, so that it is vary by the E1 and E2 is out of phase. It's an opposite direction. E1 and E2 is opposite to the 180 degree out of phase. Right. So I will explain again. So we are taking V1 as a reference, primary applied voltage. Under no load condition, we have I0, no load current, that is having two components, working component and magnetizing component. Working component in phase with the voltage, but the magnetizing component out of phase, 90 degree out of phase. This component is responsible for producing the flux. Both are equal, both are in phase. So vector sum of these two is I0. When the transformer is loaded, this I2 current is flowing through the secondary winding. Due to that, I2 dash is flowing through the primary winding. So that I2 dash is in phase with the applied voltage because of resistive load. Because of resistive load, I2 dash and V1 are in phase. The vector sum of I2 dash and I0 is the vector is I1, total primary current. Right. So this is the angle pi naught, that is the angle between I0 and V1. So this E1 and E2 is the induced EMF based on the Lenz's law. Induced EMF oppose the applied voltage, so that both are opposite to each other. In case of inductive load, the same process I0 is available, the vector sum of IW and I mu, but the I2 dash, when the transformer is loaded, we got I2 current in the secondary. So due to that, we have I2 dash current in the primary. Because of inductive load, the current in the primary is lagging the applied voltage, lagging the applied voltage. There is a lagging between the voltage and current, that is current is lagging the applied voltage by pi 2. This pi naught is the angle between W, IW and I0. That is a different thing, that is no loaded condition. This is loaded condition, there is a lagging of current is lagging with the applied voltage by pi 2. Here both are in phase, I2 dash and V1 are in phase, there is no angle, but in here due to inductive load, current is lagging the applied voltage by pi 2. Similarly, the other things are similar, E1 and E2. The capacitive load we will see later. Now we will go to the description. Take the primary voltage as a reference. We will take the primary voltage as reference. No load current I0 lagging V1 by an angle pi naught. So there is a lagging of V1 and I0 by this pi naught. The magnitude of I mu set up the flux pi, that is in phase with the I mu. I mu is at 90 degree with V1. The phase angle between I mu and V1 is 90 degree. This I mu produce the flux pi, but I mu and flux pi are in phase. Working component are of no load current IW is in phase with the V1. There is no lagging, there is in phase. Due to flux pi, an EMF is produced in the E1. Is produced in the EMF E1 and E1 in the primary, E2 in the secondary. Due to the flux, we have induced EMF E1 and E2 in the primary and secondary. EMF oppose the cause producing, so that E1 and E2 are anti-phase with V1, right. Now when the secondary is loaded, the current I2 is flowing in the secondary. When this load, I0 is the current flowing in the primary under no loaded condition. This I2 is the current flowing in secondary during the loaded condition. If the load is purely resistive, I2 is in phase with E2. If the load is inductive, I2 lags the E2 by pi 2. If load is capacitive, I2 leads the E2 by pi 2. So, based on the load, it may be in phase or lagging or leading. That already we discussed in the diagram also. When a current I2 flows in the primary, which is anti-phase with I2, because of I2 one more current is flowing through the primary winding, that both are opposite, both are anti-phase. The primary current I1 is the vector sum of I0 and I2, that also we discussed. Now we will see the capacitive load. We already discussed the resistive load and inductive load. Now we will see the capacitive load. So this applied voltage V1 is taken as reference. This current I0 during no loaded condition is a vector sum of IW and I mu. This I mu is 90 degree opposite to that V1. I mu produce the flux pi. This working component is in phase with the applied voltage. Now when the transformer is loaded, we are getting the current I2 in the secondary winding. This I2, due to this I2, one more current flowing in the primary winding is called I2 dash. See this I2 and this applied voltage V1, this I2 is leading the applied voltage because of capacitive load. Because of the capacitive load, this I2 dash, current flowing in the primary winding, is leading the applied voltage V1. In case of resistive load, in phase. In case of inductive load, this I2 is lagging. In case of capacitive load, I2 is leading. This vector sum of this I2 and I0 is nothing but the total primary current I1. Right. Similarly, this E1 and E2 induced EMF, which is anti-phase with the V1 because of Lenz's law. So in this video, we discuss about the phasor diagram when the transformer is loaded condition for a 3 different loading conditions: resistive load, inductive load and capacitive load. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening.